Geometry, Chapter 5, Section 2, Bisectors and Triangles. I'm going to try to squeeze this in 15 minutes, so get your pencil moving. Warm it up, come back and see what the answers. Okay, as we showed yesterday, when you're using a compass, you are using, you're putting that sharp leg, that sharp point down, and you're using the pencil side to form arches, right, with a given radius. So in example number 1, we have a triangle. From this vertex, the first step is to draw an arch which intersects with the two adjacent legs, right? And then from each point where the leg has been intersected, we draw a arch with the same radius, right, over in the region that we think that a ray would bisect this angle. So from here, we draw an arch, and from the second leg, we draw an arch, and where that intersection takes place, we draw a ray, and we have an angle bisector. Very good. If JK is perpendicular to ML, at a midpoint K, we have two congruent pairs of segments. J is equidistant from M and from L. So JM equals or is congruent to JL. Also, due to the fact that K is a midpoint, we can say that, and it's a midpoint of this segment ML, we can say that MK is congruent to KL, right? By definition of a segment bisector. Okay, so here are the objectives today: to prove and apply properties of perpendicular bisectors of a triangle, and prove and apply properties of angle bisectors of a triangle. Since a triangle has three sides, it may have three perpendicular bisectors. Each side is bisected bisected with a perpendicular segment. When you construct perpendicular bisectors, you find that they have an interesting property. The perpendicular bisector of a side of a triangle doesn't always pass through the opposite vertex. So here we have a perpendicular bisector, this red segment, and look at, if we were to extend it, it would not pass through the opposite vertex, right? There may be triangles where it could, but it is not a guarantee. So when three or more lines intersect at one point, those lines are said to be sharing that point. So we have this prefix con, right? Concurrent, sharing the point in this case. So we can say that the point of concurrency is the point where they intersect. In this example, it's point P. So in the construction, you saw that the three perpendicular bisectors of a triangle are concurrent. They share a point. This point of concurrency is the circumcenter of the triangle. Point P is the circumcenter of the triangle created by the three perpendicular bisectors. So we have what is known as the circumcenter theorem. It tells us that the circumcenter of a triangle is equidistant from the vertices of the triangle. So the circumcenter is formed using the perpendicular bisectors from the sides, right? And it lets us know that the distance from that circumcenter to each vertex is congruent. Very interesting relationship. So we can say that the circumcenter can be inside the triangle, outside the triangle, or on the triangle. So the circumcenter for an acute triangle, when those perpendicular bisectors are drawn, that circumcenter is inside the triangle. For a obtuse triangle, look at this, it's very interesting. The perpendicular bisectors intersect outside the triangle. Interesting. But notice that that point of intersection, which we called the circumcenter, right? The circumcenter is equidistant from each of the vertices of this triangle. Interesting. And then for a right triangle, the circumcenter is on the triangle. You see, it's on the hypotenuse here. Very interesting relationship. So we can say that the circumcenter of triangle ABC here is the center of the circle here that is touching each vertex of triangle ABC. We call that circle a circumscribed circle. Okay, a circle that contains all the vertices of a polygon is circumscribed about the polygon. Isn't that interesting? Okay, very good. So let's see what we can do with this. We have segment DG, EG, and FG are perpendicular bisectors of this triangle ABC. So find GC. So by definition, point G is called what? The circumcenter, right? Because the circumcenter is the point that is given when the perpendicular bisectors intersect. So we have G, the circumcenter, and we know that the circumcenter is equidistant from each vertex, right? To each vertex. And in this case, we're asked to find GC, which is congruent to GA and GB, right? GC is not given. Do we know GA or GB, those lengths? And we do. Look at here. We know GB is this length 13.4. Therefore, GC is 13.4. And we can also even say that GA is 13.4. Okay, by substituting, using what we know about the congruency of those segments. Okay, we're going to use the diagram here to find segment GM. Segment GM. Okay, so what we know here is that MZ is a perpendicular bisector of the triangle GHJ. So if it is a perpendicular bisector, what does that mean? It means that MZ has a right angle here, right? And it also means that it is cutting segment GJ into two congruent segments. And do we know either of the lengths, GM or MJ? And we do, we know MJ. If MJ is 14.5, what can we say about GM? Yes, it is congruent. It is 14.5 as well. Okay, we're asked to use this diagram to find JZ. Z is the circumcenter of triangle GHJ. Okay, so we're looking for JZ. You can see it's formed by using the circumcenter of the triangle to a vertex. So by definition, the circumcenter creates three segments that are congruent. A segment from the point to any of the vertices, right? So do we know the length of any of these segments? And we do. We know ZG is 19.9. Therefore, we know JZ is 19.9 and HZ is 19.9 as well. Very good. And that's using our circumcenter theorem. JZ is equal to GZ, and so by substitution, GZ is 19.9. Can I show you? There we go. Okay, we're asked to find the circumcenter of a triangle with vertices 0, 0, 10, 0, and 0, 6. So the first step would be to graph this triangle, which has been done for you. You have it in your notes. And then the second step of finding a circumcenter would be to find the perpendicular bisectors of the sides, right? Now, the vertical and the horizontal legs of this triangle are very helpful because it's easy to locate a perpendicular bisector, right? Looking at this horizontal leg, we go from 0 to 10. So if it's going to be a bisector, what is halfway between 0 and 10? 5. Good. 5. And we would draw a segment that is perpendicular to that leg, and so the slope of that segment would be undefined. Good. And so we have one bisector located, right? And then the second bisector would be on the vertical leg, right? And this vertical leg starts at 0 and goes to 6. So if it's a bisector, it's cutting this leg in exactly half. So it would be a horizontal line at 3. Okay? So that is what is said in this reasoning here. The perpendicular bisector of HJ is x equals 5, and the perpendicular bisector of HK is y equals 3. Because it's a right triangle, we know that the circumcenter lies on the hypotenuse, right? So all we have to do is graph those two bisectors and locate the point of intersection, which is there, right on the hypotenuse at 5, 3. And that is our circumcenter for this triangle, which means, interestingly enough, that if we travel from 5, 3 to 0, 6, that distance is equal to 5, 3 to 10, 0. We could use our distance formula to prove that, right? Okay, so you're experts now on the circumcenter of a triangle, and now we have a second type of center. A triangle has 3 angles in addition to those 3 sides, right? And each angle has a bisector. So if we draw the 3 angle bisectors of a triangle and locate their point of concurrency, that point is different than the circumcenter. That point is called the incenter of the triangle. Okay? The incenter theorem tells us that the incenter is equidistant from the sides of the triangle. So let's see this. So the incenter was found by bisecting each angle, right? And now if we take that point P and draw the shortest possible line to each of the legs of the triangle, we have 3 segments that are congruent. These segments are not necessarily bisecting the sides of the triangle, right? But they are themselves congruent. Okay, so this is just a little note that what I just mentioned, that the distance between any point and a line is the length of the perpendicular segment, right, from the point to the line. Unlike the circumcenter, the incenter is always inside the triangle. Let's see what this looks like. Okay, so we can see the angle bisectors locating the incenter of an acute triangle. And of an obtuse triangle, the incenter is still inside of the triangle. And finally, of a right triangle. And again, the incenter is interior. Okay, previously we had a circle circumscribed about a triangle. Now we have a circle inside of a triangle. So we can say that the incenter is the center of the triangle's inscribed circle. Inside of the triangle, we have an inscribed circle. A circle inscribed in a polygon intersects each line that contains a side of the polygon at exactly one point. So this is an inscribed circle. It's inside. Segment MP and LP are angle bisectors. Find the distance from P to side MN. Okay, side MN is over here. Well, if these are bisectors, then we know that this is the incenter. Point P is the incenter, which means if PQ is 5, then the perpendicular distance from P to side MN would also be 5, right? By definition of the incenter theorem. Okay, here's an interesting question about the measurement of an unknown angle. And so we're looking for the measure of PMN. We know that MP is an angle bisector and LP is an angle bisector. Okay, so let's just do this quickly. I'm running out of time. But if LP is an angle bisector, then this PLN is 50 degrees. And what would PLQ equal? Over here, good, 50 degrees as well, right? So we would have 100 degrees here, and we have 20 degrees there. 120 plus this entire angle, right, would be 180. So 120 plus what is 80? Okay, good, 60, right? So PMN is exactly half of 60 because MP is bisecting the 60-degree angle. So PMN is 30 degrees. Pause the video and see if you can answer this question. Okay, so this is the incenter, which means that the perpendicular distance to PQ from X would be equivalent to xy, which is 19.2.